Okay, first an announcement. In the second hour, there will be a seminar from Technokent. So there will be, I forgot the name, somebody will come and to talk about the innovation-driven entrepreneurship, or however you pronounce that word. And so we won't have a lecture in the second hour. We will go downstairs to P6 and listen to the talk. And of course, this means that we will be missing 1 hour, which I will do on Wednesday in the first hour. So those who have overlapping courses in the second hour, you will not miss anything. But on Wednesday, the first hour, we will have a lecture. Entrepreneurship is girişimcilik, inovasyon, inovasyon. Yenilikçilik diyebiliriz belki. Well, let's say, when you are preparing applications in the future, either for projects or for jobs, etc., you will know that there are all these buzzwords, keywords, let's say, that you should use in your application. They change from time to time. And in this age, two of those buzzwords is innovation. So whenever you are making an application, you should somehow try to use that word in some place in your application, and also entrepreneurship. So in a sense, here you have a title which contains 3 words, and 2 of which is one of those keywords. Okay, now we will continue with our reflection and refraction of electromagnetic waves. And if you remember, we had already studied the case when we have normal incidence. That was kind of an easy derivation. Now we have somewhat a more complicated derivation where we need to take into account the normal components, the parallel components, etc. And we had this case, well, just give me one moment. So we have this interface where we are sending an electromagnetic wave in this direction. I repeat, this is not just a point particle. I just use it to denote the direction of the wave. The wave is everywhere. It had K1, and we were looking at the case when the electric field was in the plane of the incidence. So if this is the electric field, E1, the B field is out of the screen, and this B field is parallel to the interface, reflecting surface. And there is a reflected wave, we said K1 prime, and if we still assume the electric field to be in this direction, E1 prime, then the B field is into the screen, and there will be some this is the reflected one. Some of them will be transmitted if it will be refracted. Its direction will change. It will be moving, let's say, in this direction, K2, E2, and the B field will be again parallel and out of the screen. Now, if you have seen your next homework, in the next homework you will be studying the case when not the B field, but the E field is parallel. So the B field will have a parallel component to the surface and the perpendicular component to the surface. We had already studied the Snell's law. So it's just, we have the boundary conditions to study this problem. So the reflected and transmitted waves should satisfy the boundary conditions we have. And the boundary conditions should be satisfied at every point, at every time. That was basically what told us that the angles between the reflection angle is equal to the incidence angle, and the transmission, the refraction angle is related to the incidence angle through Snell's law. So any questions on that? Of course, we still need to find the electric fields and the magnetic fields, and we will determine them again by using the boundary conditions. I mean, we had written down the boundary conditions at the end of the last lecture. Let us just rewrite them. We know that the divergence of D is 0, and hence the divergence of epsilon times E is 0, or the epsilon times E, the perpendicular component, is continuous. The perpendicular component, the epsilon times E, this is perpendicular to the boundary. That is what should be continuous. Now let's look at those. What's the perpendicular component of epsilon times E on the left-hand side and also on the right-hand side of my surface, the interface separating these two regions? Let's see, on the left-hand side, so this is Z is equal to 0. This region is Z less than 0. This region is Z larger than 0. For Z is equal to 0 minus, let's say, I'm in this region, but on the surface. There I have two electric fields. One electric field this is at the top, you see one of the electric fields we have. It is pointing in this direction. Let me write E10, meaning that I will just always assume that EI vector is EI0 vector e to the power I k dot r minus omega t, and E1 prime is equal to E10 prime e to the power I minus k, this is ki, k1 prime dot r, this is plus minus omega t. So these are, here I only, since I know that on the surface these are all equal, I can just cancel them in my boundary conditions. The only thing I need to pay attention to is these vectors over here. So this is my E10. After reflection, I have this E1 prime, 0 vector. This is for Z less than 0. Now, what are these angles? Are they equal? Are they equal to what? You see, let's see. This is my theta I, my incidence angle. Okay? So if I look at over here, this is also my theta I. This is 90 degrees. So this angle over here is also theta I. So E1 makes an angle theta I with the vertical. Do you agree? So you see, this is 90 degrees to my surface. Here I draw also the parallel line perpendicular to my surface. Since I have these two parallel lines, there is this third line. This angle should be equal to this angle. And then I draw this perpendicular line, which is parallel to my surface. Well, this angle over here is 90 degrees. So here I have a 90 minus theta I. But similarly, this angle is also 90 degrees. So if this is 90 minus theta I, this angle over here is also theta I. So the E1, the angle that the electric field makes with the vertical is theta incidence. So this is my theta I. Well, similarly, this angle is also theta I, because we had seen that the angle of incidence is equal to the angle of reflection. So these two are my theta i's. So the perpendicular component, E perpendicular, is basically Ez. And Ez is E10 times sine theta I plus E10 prime, or minus E10 prime sine theta I. This is on the left of my surface. Now, on the right of my surface, I only have the transmitted wave. So this is my E2 vector, E2 0. This is theta transmitted. I'm not repeating the derivation. Basically, the angle that the electric field makes with the vertical is the same as the angle that the k vector makes with the normal direction. So the E perp in this case, this is for less than 0, z larger than 0. This is equal to E2 0 times sine theta t. And I know the continuity of epsilon times the perpendicular component of the electric field. So basically it tells me that epsilon 1 times E10 minus E10 prime times sine theta I should be equal to E20 times sine theta t. Epsilon 2 times. Now, this is one condition we have. This is from the Maxwell's equation that the divergence of the displacement field should be 0 in the absence of any free charges. And since we are assuming that there are no surface charge density at the interface, the divergence of D should be 0 at that point. Which tells us that the perpendicular component of the electric field should be continuous across the surface. Now, divergence of B is also 0, which tells me that B perpendicular is continuous. But the perpendicular component of B is 0 anyway, because we are using in our case at least, we are looking at scattering in which B is parallel to the surface. So there is no perpendicular component. The component of B perpendicular to the surface is 0 in our example. It is not so in general, but you can always write whatever wave you have. You can divide it into two parts. One part will have an electric field parallel to the surface. The other part will have a B field parallel to the surface. And we are looking at the case when the B field is parallel to the surface. So from this Maxwell's equation, we don't get any new conditions on our unknowns. Now let's look at the third Maxwell's equation, or whichever you are numbering. Curl of E is equal to minus del B by del T. But this implies that the parallel component of the electric field is continuous. Well, this is when Z, in the above figure, we have what happens when Z is less than 0. I can use the same figure, which just tells me that E10 prime cosine theta I plus E10 cosine theta I This should be equal to, this is when z is larger than 0, E20 cosine theta t. So this is my second boundary condition.
On the left-hand side of the line, there's two waves. If we look from the right-hand side, we see just that.
Yes. So the wave is just the sum of everything. On the left-hand side, we have two things to sum. On the right-hand side, there is just one thing to sum. Well, look at the equation. It's a relation between the E and the B field. So it gives us a constraint on the E field. If you look at the previous Maxwell's equation that we used, it's an equation for the D field. That is why here we have the epsilon. Well, in fact, here we are also making the assumption that the medium is linear. If the medium is not linear, we cannot really say that epsilon times E is continuous. So this is valid. Epsilon times E perpendicular component is continuous only if the medium is linear. But the parallel component of E is always continuous. You see here, there's no assumption. E parallel is always continuous whether the medium is linear or not. And then the last Maxwell's equation, curl of H is equal to del D by del T, which tells us that, well, H is B over mu. So B over mu, the parallel component is continuous. And this is our third equation. Well, B is always parallel in our case, so we don't need to worry about the angles of B. And B, the magnitude of B, remember this, it is equal to the magnitude of E divided by V, or E over C times N. Well, this tells me that E10, well, let's see, let's look at the figures again. The incident electric field, it is pointing outward. So the incident magnetic field is pointing outward. Let's just choose it to be the positive direction of B. So E10 times N1. That is the B1, C times B1, let's say. The second one, the reflected one, it is pointing in the opposite direction. It is minus E10 prime times N1. All of this multiplied by 1 over mu1, mu of the left-hand side. This should be equal to, on the right-hand side, we have E20 N2 divided by mu2. Well, you see, if you look at, let me show it over here. This B field is pointing in this direction. This B field is pointing in this direction. They are pointing in opposite directions. So if this is the positive, let's say, x direction, this one points in the negative x direction. This one is still in the positive x direction. So if you write down the x component, which is the only component of the B field, this is plus B1 magnitude minus B1 prime magnitude should be equal to B1, well, this is B2 magnitude. Well, you see, I know certain things. For example, E, B, and K, they form a right-handed system, which tells me that well, this K cross E should be always equal to B. It might be that the electric field will turn out to be pointing in the opposite direction. I don't know that. If the electric field is pointing in the opposite direction, then B1 field will be pointing in this direction. Well, it will just amount to assuming that B1 prime is negative. So it won't really make any difference at the end of the day. Well, I'm talking about the components now. You see, here it's the vector. Here I have the vector. I'm taking the parallel component. These are in terms of the components. Well, basically because the B field is parallel to the surface, it doesn't make an angle. E field does make an angle with the surface, but the B field does not. So basically the angle that the B field makes with the surface is 0. It's fixed. So that's why we don't have any sines or cosines.
Şimdi hocam biz burada H yerine B bölünüğü yazdık ya.
Hı hı.
Şu buralarda falan neden E yerine D bölü epsilon ya da H yerine D bölünüğü falan?
You see, look at the definitions and the equations. We want to write everything in terms of the E and the B field. That's what we are trying to do. At least we want to write everything in terms of the same fields. If you want, you can write everything in terms of the D and the H field. If you want, you can write everything in terms of the D and the B field. Just choose two of them, either E or D or B or H, and write everything in terms of them to reduce the number of unknowns. So what your book chooses, what I choose will be to write everything in terms of the E and the B field. And then look at your Maxwell's equations. The first equation is an equation in terms of D. It's not something I choose. It's the Maxwell's equation. I cannot play with it. But I know that D is equal to epsilon times E. So I can write that equation in terms of the electric field, not the displacement field. But when we look at the second Maxwell's equation that we use to obtain the boundary, well, it's already an equation in terms of B. If you look at the third Maxwell's equation that we use, it's already in terms of E and B. So I don't need to make any conversion over there. Now, finally, if you look at the last Maxwell's equation, well, it's in terms of H and D, so I need to write them in terms of B and E first to reduce my unknowns. So now I have three equations for the two unknowns, E1 0 prime and E2 0. So let me just combine them first, so that I might be able to see some simplifications maybe. Let me look at this equation. Well, you see, if you look at the first line, it's nice. I have E1 0 minus E1 0 prime. N1 is common. I can just take it out. It just looks like this one. Well, there are some problems, though. Here I have the N1s. Here I have the signs. But I can use the Snell's identity. You see, what do I know? I know that N1 times sine theta I is equal to N2 times sine theta 2. This is what I know. So I can just multiply this by N1 divide by N1, multiply this by N2 divide by N2. So this I can cancel. And I am left with epsilon 1 over N1, E1 0 minus E1 0 prime is equal to epsilon 2 times E2 0, epsilon 2 over N2 times E2 0. Okay, at least I have one step. Now, do you remember the definition of n? How had we defined n in terms of epsilons and mu's?
Epsilon mu bölü epsilon 0 kök için.
Zero squared together.
So, epsilon times mu over epsilon 0 mu 0. So this is n. And what else do we know? Let's look at this. Well, what I would like to do is, may I convert this equation to the above equation? So the question is, what can I say about epsilon over n and n over mu? So n over mu is equal to square root of epsilon over mu, 1 over square root of epsilon 0 mu 0. And epsilon over n is equal to square root of epsilon over mu, square root of epsilon 0 mu 0. Do you agree? Or n over mu is equal to epsilon over n multiplied with 1 over epsilon 0 mu 0. So n over mu and epsilon over n are the same thing up to a constant which is independent of medium. Well, I can use it in my equation. You see, this was my equation. But epsilon over n is n1 over mu1 times epsilon 0 mu 0, e1 0 minus e1 0 prime. This is equal to epsilon 0 mu 0 and 2 over epsilon 2 e2 0.
Kök nasıl gitti?
Well, I have the 1 over square root over here, square root over here. If you take the ratio, it's just the square of them, which doesn't have the square root. Well, epsilon 0 mu 0 is independent of the medium, so I can just eliminate them. Well, this is nice. You see what we did? We start with this equation which involves the signs, etc. We had 3 equations. So we started with one of them, the one involving the signs, and at the end of the day, I obtained our third equation. So basically, those 2 equations are the same equation. I don't need to worry about both of them. It's enough for me to take only one of those equations. So that was kind of nice, because if you remember our discussion on Friday, we had these 2 unknowns. We don't know the magnitudes, E1 0 prime and E2 0. Those 2 things we didn't know, but we had 3 equations to determine those 2 unknowns. So either one of those equations could be written in terms of the other 2, or there is no solution to this system. But we had just seen that one of those equations can be written in terms of the other one, so we are safe. Just forget about that equation, deal with the other 2. Because that equation, well, this equation is nothing but that equation. They are the same thing. So now we have our 2 equations to solve. One is this one, n1 over mu1 times e1 0 minus e1 0 prime. This is equal to n2 over mu2 e2 0. This is one of our equations. And the other equation where was it? Is this one. E1 0 prime plus E1 0 cosine theta I is equal to E2 0 cosine theta t. Those are the two equations we have. And we need to use these two equations to solve for E10 prime and E20. So let me start with E20. Well, what I will do is, well, here I have the nice combination of the sum of the difference of the two, the sum of the two, just equate the coefficients, sum them up, I will get rid of E10 prime, and I will obtain E20. So that is what I will do first. So E10 minus E10 prime is equal to mu1 over mu2 times n2 over n1 E20. That is the first equation. The second equation tells me E10 plus E10 prime. This is equal to E2 cosine theta t divided by cosine theta e, E20. Just sum them up. Twice E10 is equal to cosine theta t over cosine theta I plus mu1 over mu2 and 2 over n1 E20, or E20, the transmitted wave has the electric field equal to 2 over cosine theta I, no, sorry, this is theta t. Cosine theta transmitted divided by cosine theta incident plus mu1 over mu2 and 2 over n1 times E10. Well, if you look at our final expression, E10 is the incident wave, that is the wave you are preparing. N1, N2, mu1, mu2, they are the properties of the medium. Theta incident is known. You can determine cosine theta t, the transmission angle, using the Snell's law. So everything here is something you can know or you can calculate. Well, let's look for E10 prime. Let's see, from that second line, E10 prime is cosine theta t over cosine theta I. E20 minus E10. Well, we already know what E20 is. Just put it over there. Times twice over and 1 minus 1 E10, which is equal to cosine theta t divided by cosine theta I minus mu1 over mu2 and 2 over n1 divided by their sum. And this is how much of the wave is reflected. Now you see, if you look at the above line, that is the E10, no, E10 prime is the reflected one. The transmitted one E2, this is the transmitted wave. Well, you see these numbers are always positive, so it's always positive. But if you look at E20, E10 prime, you see there's this minus sign over here, which basically tells me that it might be possible that that E10 prime can change sign. So the electric field in the reflected wave you see E10 is the E1 direction of E1 prime. It doesn't really have to be pointing in that direction. Maybe it might be pointing in the other direction. There's such a possibility. There's also the possibility that E10 prime might be exactly equal to 0. You see, if for certain angles this quantity is equal to this quantity, it is 0.
Bir şey geri yansımıyorsa.
There's no reflection. All will be transmitted. Well, let's look at what is that angle. For what angle E10 prime is equal to 0? Well, let's see. At that angle, cosine theta t divided by cosine theta I will be equal to mu1 over mu2 times n2 over n1. We also know that sine theta I times n1 is equal to n2 times sine theta t. So basically we need to use Snell's law. Well, we have here two unknowns, theta I and theta t. We can use the Snell's law to eliminate one of them and then solve for the other one. Well, the easiest one I can think of is just take the square, so you get the cosine squares. You can write the cosine squared as 1 minus sine squared. Let's go ahead. So this is 1 minus sine squared theta t divided by 1 minus sine squared theta I. No, sorry. This should be equal to mu1 over mu2 and 2 over n1 squared. Well, sine theta t by Snell's law is just n1 sine theta I divided by n2. 1 minus n1 squared over n2 squared sine squared theta I divided by 1 minus sine squared theta I. This should be equal to mu1 over mu2 and 2 over n1 squared. Well, the rest is basically algebra to solve for this sine squared theta I. So let's do the algebra. 1 minus n1 squared over n2 squared sine squared theta I is equal to mu1 over mu2 and 2 over n1 squared minus the same thing squared sine squared theta I, or 1 minus mu1 over mu2 and 2 over n1 squared. This is equal to n1 squared over n2 squared minus mu1 over mu2 and 2 over n1 squared sine squared theta I. And we can just extract sine squared theta I. Yeah, I mean, if you are interested, you can just put in some numbers for real systems and see what this theta I is. Basically, that theta I is some angle close to 40 degrees, especially with glass or with water is something like 40 degrees. So this angle is called the Brewster angle. So what does this angle mean? So you see here, at this, we had seen that at this angle, at this kind of wave will not be reflected, all is transmitted. So let's imagine we have some lake. There's light coming in every direction with all kinds of polarizations. We know that every polarization we can divide it into two. At least, okay, this is our lake. There's some light coming somewhere from the sky, from the sun, etc. Light is coming. We can write the polarization of this light in as a sum of two different polarizations. One polarization is one in which the wave has the electric field parallel to this surface, and the other one has the B field parallel to the surface. Now, if we are at this Brewster angle, so let's say you are taking a photograph, so there's light over there, light is coming, it's reflecting towards you. If you are at this Brewster angle, only the light that has its electric field parallel to the surface is reflected towards you. So the light that is arriving to you is completely polarized, completely plane polarized, because the other component is just zero. There is no reflection. But if it is completely plane polarized, just take a polarizer whose polarization direction is perpendicular to the polarization of that reflected light. That will eliminate all the reflected light. Now, if you remember the pictures I had shown you on last week of these pictures of the fishes in a lake, without the polarizer filter, you cannot see the fish due to the reflection. With the polarizing filter, you can see the fish and there won't be any reflection. That photograph was taken at the Brewster angle, so that the reflected light was completely polarized and that polarized light was eliminated by the polarizing filter. It's about 40-45 degrees. So you see, if this is the lake, okay, so you are assuming it's just almost completely flat. So here you are standing. Here you have your camera. Okay. With your camera, you are basically looking at the light reflected from this point or in that region. So if this is the Brewster angle, if you just point your camera in such a way that the angle that this line makes with the vertical is equal to the Brewster angle, which is typically around 40-45, it's close to 45 degrees. I mean, when you are taking a camera, you just don't measure the angle so precisely, but you know that it's somewhere close to 40 degrees. Then, okay, what kind of light will be reflected towards you? Well, it will be just the light coming from here, coming from the sky. It will be reflected towards you. Well, this light will be completely polarized. The electric field of this reflected light will be perpendicular to this surface of the plane of reflection. So that light is completely polarized and it has its electric field in this direction. Because since we are at the Brewster angle, there is another component of the light coming from here which has the B field parallel to the angle of the plane of reflection, but that doesn't reflect at the Brewster angle. It is transmitted, all of it. So this is completely polarized, and if you use a polarizing filter in your camera, you can eliminate all this reflected light. Well, you see, the light coming to the camera is one from the lake plus the reflected light. You are eliminating the reflected light, but the light that is coming from the lake is not eliminated. is not polarized. You see, you cannot eliminate transmission, but you can eliminate reflection if the initial light is polarized in a particular way. Well, you see, some of that light here is your fish. There is light underwater. I think up to 200 meters, there is light. Well, below 100 meters, you cannot see anything, because to see something below 100 meters, it has to travel something like 200 meters in the water, and all of the light is absorbed in 200 meters, more or less. When you dive, you see something underwater, right? There is light.
Hocam şimdi şu elektrik paralel dedik ya, o tamamen yansıyor mu yani?
Not completely, partially. But at least in this usage, I mean, it would have been nice if I could eliminate it completely in reflection. I cannot, but I eliminate it by using a polarizing filter.
So we can use this filter as a medium.
As a?
Medium.
The filter? No, not really. I mean, the filter just allows you to pass some light to pass, some other light not to pass. It's not really a medium. Of course, I mean, it is a medium, it's made up of most of the time glass, so that's a medium. But the important property is that it's not homogeneous. It's not isotropic. Here we are treating the lake and the atmosphere as isotropic mediums, homogeneous media. A polarizing filter is not isotropic.
If the light doesn't reflect completely in that angle, so what is the difference between this angle and other angles? Because in other angles we also have both reflection and
Okay. So basically this angle is, when you are changing the angle, let's say at normal incidence, the electric field is pointing in one direction of the reflected light. Okay? As you are changing this angle, the electric field more or less points in the same direction, but its magnitude gets smaller and smaller. And at some other angle, it just points in the opposite direction. So somewhere in between, it has to be 0. So it is this angle over here at which it is 0.
How the filter is determined which one is transmitted?
Well, the filter is a different issue. It's not a linear medium. So you cannot treat the filter as in the way we are dealing it over here.
We can also have a problem with the filter.
Well, you see, what we do in physics is you just analyze the problem, divide it into smaller parts. One problem is over here. We solved that one. And we said that, okay, when there is such a reflecting surface, at some particular angle, it's possible that at least one particular polarization is not reflected at all. Okay, that is part of the problem. The second part of the problem, well, we have these weird materials. Well, weird, not really weird. I mean, you just buy them for a couple of liras in a three-dimensional movies that we call filters. They have this nice property that they only allow one type of polarization to pass and not the other type of polarization. So we just combine the two and we can say what is happening over here. Now, do you want to solve for what happens in a polarizer? Well, then you have to know the properties of the polarizer. You can basically apply more or less the same ideology. You solve for the fields in one side, on the other side, you determine the boundary conditions. Well, you can, but you have to implement the properties of the filter. Now, after we study the reflection and transmission in conductors, for example, we will be able to describe one particular type of filter.
Hocam peki hem elektrik filtre paralel yüzeye hem de dik olan ikisini birden böyle eliminate etme imkanınız var mı? Hani hiç reflection.
Look at your solutions. Is it possible? Trust your solutions. trust in the electromagnetic force.
Elektrik ya da manyetik alanda herhangi bir yüzeylik olmak zorunda. Yani ikisi paralel olmak zorunda. Her ikisinde paralel olmadığı durumlarda.
Of course. But what I said is, even if you have electromagnetic waves in which neither the electric nor the magnetic fields are parallel, I can always write it as the sum of two components. One is parallel, one is perpendicular. And since our Maxwell's equations are linear, I can study how they will reflect independently, and then to find how it will be reflect and transmit, how the sum will reflect and transmit, I just sum the contributions of each one of the components separately. So that's why we had studied one of them. And the second one is your homework. So the strategy will basically be the same. It's just some of the equations will change. The electric field will not have a perpendicular component, but the magnetic field will have a perpendicular component. Electric field will be parallel, so the equations will change. You just need to solve the algebraic equations. Okay, so in 5 minutes, we have this seminar in P6 downstairs.